Hello everyone, this is a bonus video from me. If I'm going to be true to my principles about teaching and learning in mathematics, there's no way I can, sort of give you guys a formula and tell you that's how to solve a problem without showing you the thought process and derivation behind the formula. For this particular case, I'm talking about the quadratic formula. In problem number 5 on our assessment, you had to use the math problem. You had to use the quadratic formula to determine the roots of part B. So what I'm going to do is I'm going to show you guys how to actually derive the quadratic formula. And one thing I want all the students to keep in mind is nothing in mathematics is magical. There wasn't a guy who just sat down and was a genius and just said, the way to factor any quadratic is this formula. He actually derived it using the same rules that you guys use to solve algebra problems every day. So in order to understand the derivation of the quadratic formula, first we need to discuss something called perfect squares. Now, a perfect square is a type of, I'm sure you guys are familiar with factoring. A perfect square is the expanded form of the quantity x plus y squared. And really, the whole point of me showing you this is to give you guys an idea of how to sort of identify a perfect square. Because typically what you do, there's a very useful strategy called completing the square that's used to complete the proof. But if you can't recognize a perfect square, it's kind of hard to complete the square. So the first thing you'll notice is, like I said before, a perfect square is the quantity x plus y squared. Now, if you expand this out, the first term of x plus y squared is the first term x squared. So then you have x squared. And the second term is going to be these two terms, x and y, multiplied together, so xy, and then you multiply that by 2. So once again, the second term of the perfect square is 2 times x and y's product. So then you're going to have 2xy. And then the third term of a perfect square is y squared. So this is how you can sort of recognize a perfect square. Now, if you guys remember what the quadratic formula does, is it helps you factor any quadratic equation to find the roots. Or in other words, it helps you, let me just draw the general formula of a quadratic. Now this formula right here, which is going to be ax squared plus bx plus c. This is the general form of a quadratic. Every quadratic has a formula like this. Now sometimes the c can be 0, sometimes the b can be 0, but as long as it has one of these terms, it's a quadratic. So this is the most generalized expression for a quadratic. Now, as I said shortly ago, the whole point of the quadratic formula is to show you how to factor quadratics in this form to find the roots. Or in other words, the value of x such that this expression is equal to 0. So the first thing we want to do when we start with the derivation is to write the equation in which we want to solve. So of course we want to solve a generalized way to find the roots of this function. Now, there's 2 tricks involved to solving or sort of deriving the quadratic formula, and it all revolves around completing the square. Now, the whole method, the whole logic of completing the square is this: you have an algebraic expression that you want to simplify, and if you could just add one term to that expression to simplify it, you'll do that, and it'll make more sense as I move along. So first and foremost, I'm going to do about 2 things that don't make sense at first, but I'll go back and explain why I did these things. So the first thing I'm going to do is I'm going to multiply both sides by 4a. It's the first thing I'm going to do. So what that will give you, and I'll just rewrite this because I don't have a lot of space, since this is a long derivation. If you multiply both sides by 4a, you'll get 4a squared x squared plus 4abx plus 4ac is equal to 0, because naturally 4 times 0 is 0. Now this should already look familiar. Like, for example, this 4ac. We don't really need this 4ac, so what we're going to do, we're just going to minus 4ac on both sides. And what that'll give us is that'll give us 4a squared x squared plus 4abx is equal to minus 4ac. Now this is the part where we do the whole completing the square thing. If you look here closely, you can see a pattern here. So what I want to do real quick is I'm going to just complete the square. Now here's what we're going to do to complete the square. You're going to do something, you're going to add terms to this equation that's not going to change the value. So what we're going to do is we're going to add 0. Now, would you agree if I added b squared minus b squared, that's 0, right? Because b squared minus b squared is 0. So if I add this to the left side, it doesn't change anything about this function. So let me go ahead and do that. So I want to add here b squared plus 4a squared x squared plus 4abx minus b squared is equal to minus 4ac. Now the next thing I'm going to do to make this simpler and easier to understand is I want to just move this b squared over to this side. And see, actually it's the same thing too, to be honest with you. Because see, what you could do is you could add b squared minus b squared on this side, or you could add b squared and then b squared over here, then you know that would be 0, because if you minus b squared on both sides, it removes both b's. So you could do that as well. So this is equivalent. This would be actually the easier way of doing it. So to recap what I said, because that was kind of unclear, we want to add a term, 2 terms to this equation we had up here without changing the value of the equation. The easiest way of doing that is adding b squared on both sides, because you know if you minus b squared on both sides, you'll remove b. So you're not changing the value of this problem. So now that gets me to everything I've been leading up to this point with the perfect square. Now if you look closely at b squared plus 4a squared x squared plus 4abx, you'll notice something. You'll notice that these 2 terms are related. So for example, if you look at this, you can see that this could be equal to 2 times 2ab, and this could be equal to, 2ax squared. So let me just rewrite it really quick, and that'll make it even easier to see. Because I'm actually confusing myself when it's written in a different way. And there's no shame in doing this in mathematics. If there's something that's kind of confusing, because this happens all the time in proofs and derivations, if it's sort of out of order, it's kind of hard to think about it. So let me just reorder it really quick, and then it'll be kind of obvious what I'm doing at this point. Okay, so now we have b squared plus 4abx plus 4a squared x squared. Now, like I was saying before, the form of the perfect square, here's what we notice. We have a b squared. The b squared is by itself. And it's the very first term in this quadratic. So if this were to be a perfect square that we're trying to create to simplify this expression that we have, then this would be the first term in our perfect square, which would be b. So we could write right here, if we were to simplify this, b. Now we want to figure out what the second term in this perfect square is. Well, if you notice, if you look closely, the second term, you have 4a, b, and x. Now, the 3 terms that are different are the 4, the a, and the x. And over here, you have a 4a squared, x squared. The way to make this a square is to see that this perfect square would be created by taking b plus 2a, b plus 2ax and squaring that. And let me just explain again. So let me just explain it this way. This will make more sense. The first term squared is going to be the first term of our expanded quadratic. So it's going to be b squared. Then you're going to take the product of these 2 terms in the parentheses. So it's going to be b times 2ax, which is going to be 2abx. Then you multiply that by 2. So you're going to get 4abx. Now you're going to take, for the last term, you're going to take the square of the second term, which is 2ax, which will give you 4a squared x squared. So as you can see, we've sort of created a perfect square out of nothing. By adding something to the equation that doesn't change the value of the equation, we were able to create, or in other words, complete the perfect square. Now what this allows us to do is it allows us to further simplify the problem for simplicity. So as you can see here, now we have the quantity b plus 2ax squared is equal to b squared minus 4ac. Now we can take the square root of both sides. And what that'll leave is b plus 2ax is equal to plus or minus square root of b squared minus 4ac. Now it should be looking sort of familiar. Now everything we've done up to this point is just using algebraic rules. So that we didn't do anything fancy aside from completing the square and multiplying this whole function by 4a in the beginning. And I'll get back to that shortly after I finish this derivation here. So see, now what we want to do is we want to isolate x, because once again we're trying to find an expression for x that will make this expression up here equal to 0. So now we just want to get x by itself. So all we got to do is we have a minus b on both sides, and we have to divide by 2a. And what that gives you is x is equal to minus b plus or minus the square root b squared minus 4ac all over 2a. So as you can see, we derived the entire quadratic formula from just using basic algebraic rules. Now the reason why we multiply by 4a is something about a special form of a perfect square. It's just something that you'll notice. And the way that I best can explain that is by showing the perfect square of x plus 2. So if you take x plus 2 squared, the perfect square result will be x squared plus 4x plus 4. And see, this if you look at this, you can sort of intuitively, this is where the leap comes in. And this comes from just experience with working with math and working with algebra. Eventually you'll get to the point to where you can sort of see, okay, so if x plus 2 quantity squared is equal to x squared plus 4x plus 4, then maybe if I take a squared plus bx plus c and multiply this by 4a, I can get a perfect square that's reminiscent of 2. Because if you notice x plus 2 quantity squared. Because if you notice here, we have a 4 and we have a 4. We have two 4s. So we have a 4abx and we have a 4a squared x squared. So you can see how that's sort of reminiscent of x plus 2 quantity squared. And by multiplying by 4a, we were able to get a square term over here, the 4a squared x. And we were able to get the term where we have the two terms. Let me say it again. We were able to get this second term, 4abx, by creating two other terms, b plus 2ax, whose product is 2abx, which is doubled, equals this. So it's kind of confusing when you think about it. When you see it, it doesn't make a lot of sense. But if you start working through it, it'll make a lot more sense. And of course, what I surmise happened when somebody tried to solve this problem, they didn't initially multiply both sides. They didn't multiply ax squared plus bx plus c by 4a because they had no reason to do so. They just didn't know. So what most likely happened is they just started out with ax squared plus bx plus c is equal to 0. And they probably just minus c on both sides. So then they get ax plus bx is equal to minus c. You can't really do anything from here. I mean, you can pull out x, but I mean, that's not going to help because you're going to have x times the quantity ax plus b is equal to c, but I don't know what c is. So that, and if you do that, you can't really get x by itself. There's no way to get x by itself because both of these terms have x in it. And if you do what I just said, ax plus b, this isn't helpful either because there's no way I can isolate the x. I can't divide this on both sides because I want to have x is equal to something that has x in it. So if they were to go forward with the sort of logic of let me reduce this to something and isolate x with just ax squared plus bx plus c equals 0, they would get to this dead end. There's no way to isolate this x. So what they must have thought is, what if I can multiply ax squared plus bx plus c by something such that I can create a perfect square? Because if you create a perfect square, you'll get two terms in which x is only attached to one of those terms. That's exactly what we did by completing the square here. We have b plus 2ax. X is only one term. It's only on one term in this entire expression. So after we take the square root, we just have b plus 2ax. And it's very, very easy to isolate that x. And like I said, this is just the whole thought process behind this, which is mathematical maturity. Whoever derived this was experienced enough with mathematics such that when they got to this dead end, they said, let me just complete the square. And what that resulted in is a general expression that can tell you how to derive the values of x such that the polynomial you created with the quadratic formula is equal to 0. And that's the whole thought process behind the quadratic formula. So now if you have any friends in class who use the quadratic formula, you can go up to them and say, I actually know how to derive the quadratic formula. I understand how it was created, not just why it was created, but how it was created. And if you approach math this way, instead of taking things at face value and just regurgitating them and using them to solve problems, and you actually hold yourself accountable to understand how these things were created and don't just take them as face value, they're magical, it's much easier to be successful as a mathematics student. So there's basically the quadratic formula explained.